In this video tutorial, I will show the fundamental machine learning concepts for total beginners in this field. I will show the machine learning the way I would like to be taught when I started my machine learning journey. This video contains theoretical aspects of machine learning and practical part as well. How do machines perceive the world? Day 1. Why everything becomes a number. Learning objectives. Understand why machine learning transforms everything into controlled numerical ranges. Learn the fundamentals of derivatives, the language of change. Learn the gradient descent method following the slope. Learn about gradient explosion and vanishing problems. Master basic normalization techniques. See real-world applications of data transformation. Why machine learning needs bounded numerical values. Why unbounded numbers break machine learning. Introduction. Machine learning models learn through optimization, specifically the gradient descent method. When we have features with very different scales, example age 25 versus salary 50,000, the gradients become unstable. Large values cause gradient explosion, while very small values leads to gradient vanishing. Source code. Why unbounded numbers break machine learning? I will use NumPy for numerical operations, import NumPy as NP, and I will show the problem unbounded numbers break machine learning. I will use tiny value, normal value, and a huge value. And I will calculate the gradient for function f of x equals x squared. And the gradients are nothing more than just derivatives. So in that case, we will have 2 times our tiny value. And the same goes for a gradient for normal value and for the huge value. So I will just simply print in a console problem unbounded numbers. And in here I will put tiny value and the gradient for the tiny value. And the same for normal value and the huge value. To run the code, I will just simply hit Shift Enter and we see the output, and the tiny value is really small and the gradient as well. So the normal value is 1 and the gradient is 2, which is the derivative. And we have the huge value and the gradient for the huge value. And the gradient ratio, difference of a huge number of x. One learning rate cannot work for all. Gradient descent. Introduction. Machine learning models learn by adjusting their parameters, weights and biases to minimize error. The adjustment is done through gradient descent. In example, small steps in the direction that most reduce error. The size of these steps depends on the gradient slope of the error function. When features have very different scales, 2 key problems arise. First problem, gradient explosion. When input values are very large, example 1 million, gradients become enormous. The learning algorithm then takes gigantic steps, overshoots the optimal solutions, and bounces chaotically without convergence. Second problem, gradient vanishing. When input values are very small, example 0.00001, gradients become microscopic. The learning algorithm then takes nearly imperceptible steps, barely approaching the solution. Training becomes extremely slow or stops completely. Source code, gradient descent, introduction. I will use NumPy for numerical operations, and I will import NumPy as NP and show simple introduction to gradient descent, minimizing the function f of x equals x minus 3 squared. As a starting point, x will equals minus 2. The learning rate will be 0.1 and the history will start with the x value and I will update it each time. All the code is done in the for loop in 10 steps. For each step, I will use a loss function, which is x minus 3 squared, and the derivative, the gradient for this, which is simply 2 times x minus square, and I will use the update rule where it's minus learning rate times gradient, and I will add this x with the update and append it to the history to show it later. The update rule is simply the formula that tells us how to change x so that the loss function decreases. So the function plays the role of loss function. The gradient tells us in which direction f of x increases. The update is a move in the opposite direction so that f of x decrease. Loss function, how wrong the model is. Gradient, the direction and strength of the error. Update rule, the adjustment of weights to reduce the loss. Update rule equals errors correction. Its goal is to minimize the loss function. To execute the code, I will just simply hit Shift Enter and we can see gradient descent steps. For the x value minus 1, the f of x is 25. The gradient is minus 10 and the update is 1. For the second step, the x value is minus 0.2, the f of x is 16, the gradient is minus 8, and the update is 0.8. So the target was x equals 3, but the final result is x equals 2.463129, which is good enough. Slope versus derivative. Key difference. Understanding slope and derivative is the fundamental concept that is often confused. Slope refers to linear equations and its constant. For a line y equals m times x plus b, the slope m is the same at every point. Regardless of where a point is on the line, the rate of change is constant. Example, y equals 2 times x plus 3 has a slope everywhere equal to 2. Derivative refers to nonlinear equation and is a function. For a curve y equals f of x, the derivative f prime of x changes at different points. The rate of change depends on the point's location on the curve. Example, y equals x squared has a derivative equal to 2 times x, different for each x. Metaphor, slope. Walking on straight ramp, the steepness never changes. Derivative, walking on a hillside, the steepness changes as you walk. Source code, slope versus derivative. Key difference. I will use NumPy for numerical operations, import NumPy as NP to show that slope constant for linear function and derivative changes for non-linear functions. So the linear function is y equals 2 times x plus 1. The x value is from np.line_space, which returns the evenly spaced values in the range. And in here is the function. Slope is constant, equals to every. So doesn't matter if we use slope for x equals -2, or x equals 0, or x equals 3, slope is constant and equals 2. The derivative changes for nonlinear functions. Nonlinear function in here is y equals x squared. So in machine learning, we use nonlinear functions. And the function is in here, and the derivative changes because we have 2 times x. So for x equals -2, we have 2 times -2. For x equals 0, we have 2 times 0. So derivative is a function, changes with x. To run the code, I will just simply hit Shift Enter, Shift Enter, and we see the results. So linear function y equals 2 times x plus 1 is always 2, is constant. But for nonlinear function like y equals x squared, we have different values because derivative is a function changes with x. Why this matters in machine learning? In machine learning, most lost functions are nonlinear, like quadratic logarithmic, which means the gradient derivative changes depending on position in parameter space. Near the minimum, gradients take smaller values. The curve flattens. Far from the minimum, gradients take larger values. The curve is steeper. This phenomenon causes gradient descent to naturally slow down as it approaches the minimum. Source code. Why derivatives matter in machine learning. I will use NumPy for numerical operations. Import NumPy as NP. Example loss function is L equals prediction minus target squared. Target is 10 and the prediction is array of values 5, 8, 10, 12 and 15. I will run the code in loop in the array of predictions, and for each prediction I will have loss, which is prediction minus target squared. I will have the gradient, which is derivative, and in our case is 2 times prediction minus target. And I will print out the prediction, the loss, and the gradient, and some information later. To run the code, I will hit Shift Enter, and in here we have why derivatives matter in machine learning. The loss function is L, which is prediction minus target squared, and in here the values prediction 5, the loss 25, the gradient minus 10, the prediction 8, the loss 4, and the gradient minus 4. And the gradient tells us if the gradient is negative, increase prediction. If the gradient is positive, decrease prediction. If it's 0, we are at the target. Derivatives, the language of change. What are derivatives? Before understanding gradient descent, we need to understand derivatives. A derivative tells us how much something changes. When we minimally change the input value, it's the rate of change or slope at the given point. Think about it like we're driving a car. Our position changes over time. Our velocity is derivative of position. It tells how fast our position changes. Our acceleration is the derivative of velocity. It tells how fast our velocity changes. In machine learning, derivatives tells us how error changes when we adjust model parameters. Mathematical foundation of derivatives. For a function f of x, the derivative is defined as f prime of x equals limit when h approaches 0, and it is f of x plus h minus f of x divided by h. This means how much does f change when a minimal change is introduced to x. Simple example. First, constant f of x equals 5. Derivative f prime of x is equal 0, meaning constant values don't change. Second, linear function f of x is equals 2 times x plus 3. Derivative f prime of x is equal to, meaning for every increase of x by 1, the value of f increases by 2. Third, quadratic function f of x equals x squared. Derivative f prime of x equals 2 times x, meaning the rate of change depends on the current value of x. Fourth, cubic function f of x equals x cubed. Derivative f prime of x equals 3 times x squared. More will be discussed in the section partial derivatives, multiple features, multiple gradients. Source code, mathematical foundation of derivatives. I will use NumPy for numerical operations, import NumPy as NP, and I will use three functions: normal function, numerical derivative, and analytical derivative to depict the derivatives. So the f of x is just an example function like loss or activation used in machine learning for calculation demonstrations. The numerical derivative approximates gradient using definition in machine learning used for gradient checking. And the analytical derivative, exact gradient determined by differentiation rules in machine learning used in training back propagation for fast optimization. So function is x squared. The numerical derivative is just f of x plus h minus f of x and divided by h. And the analytical derivative is just the derivative of our example function. For this example, I will use some test points, which is an array of numbers -2, -1, 0, 1, 2, and 3. And I will go in the for loop over these points, and for each x value, I will use our functions, the example function, numerical derivative, analytical derivative, and I will print out the values. To run the code, I will just click Shift Enter, and there it is. Definition of derivative. For simple function, when the x input is -2, we get 4. For the numerical derivative, it's -3.9999. And for the analytical derivative, it's just -4. And it's the same for other values.